Good morning, everyone.
Good morning.
How you doing today?
I'm good.
Glad to hear that.
Still getting my iPad set up.
I just barely made it today. I
Yeah.
scooted in, looked at the clock, went, oh, 5 seconds left. And
Yeah.
then quickly had to punch a button.
Me too.
So how are things going with your assignments?
So far, so good.
Going pretty good?
Yeah.
So I think what we're going to do today is I'm going to continue my practice of kind of doling out the pieces that you're going to need for finishing up the big assignment coming up, which is to be able to crack passwords really quickly. So we've learned last time how to create a dynamic array, one that can grow as you need it. And I guess that was the main part of it. And I was hoping last time to get to structs, the ability to store multiple pieces of information inside of one variable, but we didn't get to that. So we're going to do that today. So we'll talk about structs, how to declare them, how to create a structure, how to put things into it, how to get things out of it. And then we'll see about what time is left over. And then maybe we could do something like an array of structs. Ooh, right? So we've got a complex data structure. We've got an array, and inside the array, we've got another thing, like a structure. So that's my goals for today, but we'll see how far we get. So before we begin, do you have any like lingering questions, comments? Got stuck on an assignment and want some help? That's what we're here for. Is we can do that. We can, if you're stuck on an assignment, we can bring it up on the screen and we can take a look at it and we can try to, debug it as a group. No, you're all good?
No, yeah, I'm doing okay.
All right. Well, then we get going on this. right, so we have, so a struct, like you said, in C is a way to declare a structure kind of like a Java class. You know, in a class, you can put things into it. You can put fields, or what are called instance variables. They can hold things like, if you're declaring a class to hold information about a person, it could be a person's name, their age, their address, phone number, you know, any information you want to store about that person. But the thing about a structure or a class is that all those instance variables don't all have to be the same type of thing. You know, the names could be strings, and their age could be an integer, and their address is also a string. So you can put a variety of different types of things inside of a class or a structure. And so that's different from an array. An array, all the things have to be the same kind of thing. You know, they have to be all integers or all strings. So a struct allows you to make a heterogeneous data structure where you can put multiple kinds of things inside of it. So let's start with just a basic one. Here we go. So here I have defined a structure called GPS. So the way you define a structure is you put the word struct and then the name of that structure, kind of like in Java you would say class, and then the name of the class. Then an opening brace, and then inside of the braces you just put in the variables, and these are just variable declarations. You've got the type, you've got the name of it, the semicolon after each one. Then a closing brace, and then here's one of the few places in C where you're going to find a semicolon after a brace, right here. That ends the structure declaration. So you do need this semicolon here or it's not going to work. And then once you have declared the structure, you can then use it in your program. And you declare a structure variable the same way you declare like an integer variable or a float variable. You just put the type in front and then the name afterwards. Except that now the type is two words. The type is struct and then whatever it is, in this case GPS. So we're going to put struct GPS in front. That's the type. And then the name is, in this case, it's Amazon. I looked up the latitude and longitude of Amazon's corporate headquarters in Seattle. So I created a variable called Amazon that's a struct GPS, and then I can assign to the latitude and longitude by just assigning them using equals, but I'm going to use the dot to access the fields within the structure. So I've got Amazon as the structure, and then a dot, and then the field name, latitude and longitude. So it's very similar to using an object in Java. You use that dot notation to access the fields within the object. So in fact, that's where Java got it, right? The C came first, and so the C declaration for structures was kind of carried forward to objects in Java, except that they're called classes instead of structures. The difference between a class and a structure is that in Java, a class can hold not only instance variables, but can also hold methods. And a struct in C only holds instance variables. It doesn't hold methods. So that's the primary difference between the two of them. C++ is kind of a hybrid between the two of them. You do have structs and you have classes. So you have both of these things that exist in C++. Java did away with the structs entirely, and C, of course, doesn't have classes. So C++ kind of sits in the middle where it's got structs from C and it's got classes like Java does. So let's try that out in a program. So typically, in a C program, you're going to put your struct declaration up at the top. It's not going to be within a function. You could put one there, but typically it's done at the top above the functions because you want most likely you're going to want this structure definition to be accessible throughout your program, no matter what function you're in. There's that semicolon at the end of the structure declaration. And then inside my main, I can say struct GPS Amazon, and then Amazon.lat equals 47.614, and Amazon.lon equals negative 122.340. And then if I want to print these two values out, unfortunately, I can't just pass in Amazon and just have printf print it out, because printf doesn't know what to do with an Amazon thing. It's never seen a struct GPS before. So you're going to have to break it apart into its constituent pieces in order to print it out. Let's do Amazon is %f, comma, %f. So here I'm printing out two floats, the latitude and the longitude. All right, let me save it and run it. And there we go. Now you can see that floats get rounded. I put in 47.614 and I rounded it to 613.998, and the 122.34 got rounded to 122.339996. But that's close enough. That's as best that a float can do. Seem pretty straightforward. Just like with any other variable in C, when you declare a struct up here, or create one, the values that go inside the struct just have junky values to begin with, right? You can't assume that they're all going to be set to 0 like a class in Java. So they're going to have just garbage values, and then it's up to you to assign them. Now, you could actually assign the fields of a structure at the time that you'd create it by just simply, let me put comments in front of here. You could just simply say equals, and then inside of curly braces, you could just list out the two values. The first value will go into the first field, and the second value will go into the second field. So notice that you don't name the fields anywhere in here. You just pass in the values, and then they just go in order. So that still works. We can create another structure. And I didn't get a chance to look up any other locations. So give me a like a famous landmark. We'll go look up the location of it. I was looking up the Golden Gate Bridge. We could do that. So here's the latitude and longitude right there. I already forgot what it was. 37.819. And negative 122.48. Okay. So there we go. So, what I noticed here was I'm printing out two structs, both of the same type. They're both GPS structs. And my printf statement is pretty similar. I'm passing in two %fs for my floating point placeholders. And then I just pass in the name of the structure, .lat, and the name of the structure, .lon. It might be a good idea, since I'm doing basically the same thing twice, to make a function out of this. Make a function called print GPS that takes in one of these GPS structures and then just prints out the values that are inside of it. So let's do that. Let's make a function called print GPS. And let's actually spiff it up a little bit. Let's have it take two parameters. The first parameter is going to be the string to print out in front of the colon. And then the second parameter is going to be the actual GPS structure that we want to display. There's a question here. Do structures always have to be declared before main, like in Python? Well, they have to be declared before you use them. So main uses the struct GPS, so the declaration of struct GPS has to come, at least above line 13. So usually it goes up here. So usually, yeah, it goes at the top, just because you want all parts of your program to be able to know what a struct GPS is. And then the next question is, can you prototype this? Absolutely you can. I'm glad you asked. That was kind of like where I was thinking we would go with this. Is maybe we can take all the stuff that has to deal with GPS structures and move it into a separate file. But let's kind of get all the pieces together first, and then we'll do that. Let's call this the string. Let's call it S, and then struct GPS. Let's call it G. And then all this does here is it basically does this line, except that we're going to put a string right here, and then we'll change this to G. Okay, so all this does is it prints out that string in front of the colon, and then the two floating point numbers come afterwards. And we're just passing in the whole structure. Just pass in that GPS structure, and then the print GPS function is going to access the individual fields within it. So that means down here we don't have to call printf. We just call print GPS, pass in our little prefix string, and then pass in the structure itself. And then down here we'll do the same thing. I'll save it, compile it, and I didn't put the type in front of the function name. And since this doesn't return anything, it just simply prints something out, I'm going to put void in front. And I still have an error. I'm going to let you debug that one.
You didn't add the string.
Didn't add the string up here, right? I always feel a little bad when it doesn't compile. I take a quick glance at the error message and go, I know exactly what I did, right? And that's because I just have years of experience of looking at error messages and also kind of remembering in my head what happened as I was typing things in. And I quickly see that. I go, oh yeah, I recognize that line. Oh yeah, I see what's going on. And I can, like, within a second or two, know exactly what's going on. And so I tend to just, like, fix them. And I have to kick myself every once in a while and realize that from the student's perspective, your perspective, it doesn't work like that. It maybe you see that error message and you don't quite know what's happening. And so I need to remind myself to pause every once in a while and let you look at the error message and figure out what's going on. Because that's your reality. You look at the error message and you may have no idea what's going on. Some of you don't even look at the error messages. Did I ask you that at the beginning of the semester, whether or not you look at the error messages?
I don't remember.
I don't remember either. I usually kind of take that survey at the beginning of the semester and I ask the students, do you look at those error messages? And usually the results I get back are, no, we don't look at the error messages. And I guess I understand why. I finally queried the students enough that some students spoke up and said, hey, the reason why we don't look at the error messages is because we come out of the Java class and the Java error messages are inscrutable. You look at those error messages and they mention things in the error message and you have no idea what those things are. A very common error message that a beginner gets in Java is class enum or interface expected. And you see words like enum and interface and you've never heard those before, and so you have no idea what those mean. And so you just kind of, as a trained behavior, you just stop looking at the error messages because they don't make any sense. And then you, and I'm speaking you generally, the student then does what I call debugging by staring at the program. Bring it up on the screen and just stare at the screen until you try to figure out what's going on. And that's a terrible way to debug a program. Just kind of like hoping that you happen to see what's happening somewhere in your 100 lines of code. So I asked them, I said, do you even pay attention at all? Even if you don't understand the error message, do you look at what it's trying to tell you? And this learned behavior is just, no, we just don't at all. So I was a little surprised by that. And then I said, well, you know what? The C compiler's error messages are actually pretty good compared to the Java compilers. I understand the Java compiler's error messages sometimes are unintelligible. You don't understand what's going on. But the C compiler one, because the language is simpler and it doesn't have a lot of extra stuff like interfaces and classes, then the error messages are a lot more straightforward. And the Clang compiler's error messages are really good because they actually point to where the problem is. And then I said, if anything, even if you don't understand what the error message is telling you, at least look at the line number. And that'll help focus your attention so you're not doing the debugging by staring at the program technique, which is to kind of start at the top and just kind of look at everything and see if you can figure out what's going on. At least if you knew it was on line 11, you didn't have to go and look somewhere else. The error may not be exactly on line 11, but it's likely to be pretty close. It's certainly not going to be further down than line 11. It could be slightly above it, maybe on 9 or 10, but it's not going to be way down here, and it's not going to be way up here. It's unlikely to be that. And so I think one of the good outcomes of this particular course is by the end the students are actually looking at the error messages and actually paying attention to them, and at the very least looking at that line number so they can focus their attention into the right spots. Sometimes if you don't understand, I'm looking at a comment here, sometimes if you don't understand what the error message is, you can just copy and paste it straight into Google, and there might be an answer somewhere on Stack Overflow about what that error message means. The trick with copying and pasting error messages is that you have to be familiar enough with the error message to know what is kind of boilerplate in the error message and what is specific in that error message to your program. You could get an error message that mentions something specific to your program, like a variable name or a number that is in your program. And then when you Google that, that variable name is not likely to be in the Googleable error message. And so you might have to maybe only copy and paste part of the error message and omit the piece that is specific to your program, or you can do something like swap in a generic name there, like here. Format specifies type character pointer, but the argument is type float pointer. You might be able to Google that, but this one here is specific to my program, and so is this one here. So I might just have to omit this and hope that the rest of the error message catches enough of Google's attention to be able to put me to the right spot. Or I could swap in here and just put something generic like string, or here I could put number, something like that. And then hope that somebody has posted a question where they've done the same thing. They've swapped in those generic words, and then it helps Google kind of find the answer. So yeah, Googling error messages can be a good technique. It's just it's fraught with a little bit of danger because sometimes the error message is just specific to your program. I think it might even be Python. Some of those error messages are really kind of ungoogleable because they tend to span multiple lines. The error message does, and so it's hard to copy and paste an error message that's 5 lines long. And also, sometimes they can contain things like memory addresses that are specific to your program. And that makes them much harder to find in Google. So you have to omit that part of the error message that contains that sort of stuff.
So they just released Python 3.11 like last week or the week before, and one of the main features of it was that they improved their error messages.
Oh,
so I haven't looked at it yet.
I'll go check that out. Python's error messages are just absolutely awful.
Yeah, I think they realize that.
I wish they would realize it earlier, because Python is now, like, for more than half of the universities and colleges out there, the beginning programming language. And so language designers are really kind of stuck in this position where, first of all, error messages are really hard to write. Really hard, because the compiler's job, when it goes through and parses your program, the compiler's job is not to find the errors, it's just to validate the program. Really, the output of a compiler is just the executable or nothing. It either is a valid program, and then you can generate an executable from that, or it's an invalid program, and you can do nothing with it. And so being able to go back and find what's wrong with it, and then give a suggestion about how to fix it, is really difficult. Really, really difficult for compiler writers to do. I learned that taking my compiler construction course. I mean, my first stab at the compiler really just outputted true or false, right? It either was a valid program and it gave you the output, or it was an invalid program and it did nothing. And then one of the assignments was, try to go back in your compiler code and at least insert maybe 5 or 10 error messages to catch common errors, like you forgot a semicolon or the parentheses wasn't closed. And it was really hard to do that, to really find where that's happening. And if you want to catch mismatched parentheses, you have to remember, okay, I saw an opening one, and I have to set a flag that says, whoop, I found an opening one, and then I didn't see the closing one, right? And so you got to throw in all this extra logic to think about how can my compiler catch errors that humans make. And part of it is, like I said, having these extra variables to keep track of what it has seen so far and what it's expecting to see and didn't see. Because the parser's job really just outputs a Boolean value. Yes, I was able to parse it, or no, I was not. And to get it to produce something other than that, really hard. Anyway, so I'd be interested to see what Python has done and how they've improved that. Because like I said, the Python developers may start out saying let's just produce an error message that an experienced developer could look at and understand what's going on. But writing error messages for beginners, I mean, if writing error messages for experienced people is tough enough, try writing one for a beginner. And you really have to think about what are the kinds of errors that beginners make, which are not the same kinds of errors that experienced developers make. And then write error messages that are useful, helpful, and kind of lead the programmer to the solution, to fixing it. There's another comment here. It says, once the error was in a function, had to delete all the object files, the .o files, from the make file to resolve the error, and made only an executable program. So there was something wrong with the linking phase, and the error message didn't tell you anything. All right, so where were we? We left off with fixing this problem over here. Okay, so we put in this string right here, and hopefully that has fixed the problem. So I'm going to save it, and we'll compile it again, and that seems to have fixed the problem, so let's give it a try. Yes, it works great. So now I've got a function for printing out one of these GPS structures, and then we're going to get out of the suggestion, which was, can we put this in a separate file so that we don't have to type struct GPS every single time. And let's go ahead and do that. So let's make a new file, and we'll call this gps.h. And I don't know if I pointed out before, but header files, the .h files, are just C files. They contain C code like anything else. There's nothing special about them. It's just that they're called .h files so that programmers know these are the things you're going to put in your include lines. So I'm just going to take this struct GPS declaration and pull it out of here and drop it right into here. Oops, my copy paste didn't go well, so I'm going to retype it. Don't forget the semicolon at the end. And then here, I can just say include gps.h, and I'm putting it in quotes so that it looks in the current directory, not in the system compiler directories. I think I've brought it up before. When you put in an include statement here, I shouldn't call it a statement. When you put in an include preprocessor directive, the preprocessor simply opens up that file, copies out the contents, and pastes it right where that include was, as though those lines were there all the time to begin with. So by moving this struct declaration out of the C file and into the H file, and then including the H file, I'm really just putting things back to the way they were. In other words, the C program thinks that my struct declaration is actually right there in my program. Anyway, let's go ahead and compile this, and it compiles just fine. And run it, and we get same output. But another thing we might want to do is this print GPS. That's also a pretty useful function that anyone who's using this struct GPS would probably also want to be able to print it out. So I could take this and also drop it into my H file, but that's not really what header files are for. Header files shouldn't, by convention, contain any actual code, like printing things out. They should only contain structure declarations, global variable declarations, defines, prototypes, not any actual code itself. So what I'm going to do is I'm going to take this print GPS function and drop it into its own C file, because it contains actual code. Now, unfortunately, I didn't have the foresight to call this gps.c file something else, because it includes a main. So what I'm actually going to do is I'm going to pull this main out and put it into something different. Let's call it gps main.c. So pull it out of there, drop the main into here, and now gps.c contains the function print GPS. It needs to include standard.io.h because standard.io.h includes the function prototypes for printf, among other things. Okay, so let's see how to get this whole thing compiled. I've got GPS main, which contains my main. I've got gps.h that includes the structure, and I've got gps.c that includes the function. Let me save everything. And now let's get it compiled. I'm going to take these two C files, GPS main, which contains my main, and gps.c, which contains that print GPS function, and it doesn't work. All right, so what's going on here? I guess what I could do, instead of trying to compile everything together at once, is let's compile each one of the pieces separately and then bring it all together. That'll help isolate the problem, right? Maybe the problem is in GPS main, maybe the problem is in gps.c. It looks like actually the problem is in GPS main because that's where all the error messages are coming from. So I guess we can focus our attention there. So GPS main. See, okay, so even though I listed both of the C files on the command line, the compiler actually does break it up into those individual pieces. It's going to compile GPS main, and then it's going to compile gps.c separately, and then it's going to bring them back together. So it doesn't actually combine these two C files into one giant program and then compile that. It really does break it up into its individual pieces, compile each one separately, and then bring them together at the end. So that means GPS main itself has to be compilable as it is. And the problem is it's not, because it includes things like calls to print GPS, which are not declared within here. And it includes reference to struct GPS, which is not defined anywhere in here. So when we compile GPS main, it says, I don't know what these things are. And then it complains. So to make this work, we're going to have to include gps.h, which contains the struct declaration. And we still get an error, or two. Yep, we still get an error. It says that print GPS has an implicit declaration. And again, I don't remember if I've talked about what implicit declarations are, so I'll say it again. An implicit declaration is when the compiler goes through your program and it runs across something it hasn't seen before. In this case, it's a function called print GPS. It knows nothing about this. There's nothing in here that tells it what print GPS is. If we go into the gps.h file, there's nothing in there that tells it anything about print GPS. So the implicit declaration says the compiler is going to take a guess about this function. It's going to guess. It's going to guess that the name is called print GPS. It seems obvious. And it's also going to guess that it takes two parameters. The first parameter is a string, and the second parameter is a struct GPS. And it can tell that by looking at what types of variables these are. So Amazon is a struct GPS. It can see that in the program. And Amazon in quotes is a string because it knows that quotes mean strings. So it's going to guess that print GPS takes two parameters, a string and a struct GPS, and also that it returns nothing because we're not assigning its return value to anything. So that's what an implicit declaration is. It just, we're not explicitly declaring what this function is. We're implicitly declaring it by having the compiler guess. And then it generates a warning because it turns out its guess was correct. It correctly guessed that this takes in a string and a struct GPS, and it returns nothing. And that happens to match the actual function declaration. It takes in a string, and it takes in a struct GPS, and it returns nothing. And so that's why it ended up just returning a warning. It says, hey, I took a guess, and it turned out I was right. So I'll let that slide. Now, if it took a guess and it was wrong, then it'll generate an error, and the compilation will stop at that point. But this was close enough that it let it slide. Nevertheless, we want to get rid of that warning. So inside of GPS main, we have to tell it about print GPS. Now, I don't want to drop the entire function in here. I just need a prototype for it. That's all main needs to get it compiled. It's just to know what the name is and what the parameters are. Main doesn't actually have to know how the function works. All it needs to know is how to call the function, what parameters to pass in, and what's expected to come back. So I can put in a function prototype here. Void print GPS. I know it's going to be a character pointer, and actually it doesn't really matter what the name of it is. We just need to know it's a string, and we know it's going to be a struct GPS. And I don't care what the name is. I just need to know it's a struct GPS. And at this point, it should compile, and it does. Okay, so you're with me so far? The reason why the compiler said that it was an implicit declaration is because there was no declaration anywhere in main about what print GPS is. So all we had to do was put in a function prototype, and that was good enough. But I'd rather not do that as well. I'd rather not put the function prototype in my main. I'd rather have the function prototype over in this header file. So we can do that. I'm going to pull this out, and I'm going to drop it right into gps.h. Let me save all the pieces, and then it compiles and it runs. So by including gps.h in my GPS main, I do two things. I bring in the declaration of what that structure is, and I bring in the function prototype or prototypes of any functions that use that structure. Notice that the function prototype doesn't have to have variable names that exactly match. The only thing that has to match is the name of the function and the types. The character pointer and the struct GPS and the void. The actual names of the parameters doesn't matter to the caller. The caller doesn't have to know what those variable names are called inside the function. All it has to know is what are the types of things that have to be passed in. So you can call them whatever you want in the function prototype. However, it's conventional to give it the same names, just so it matches up. Okay, and the the last thing I wanted to point out here is, notice that this main doesn't include standard.io.h, and yet it worked without any warnings or errors. It doesn't include standard.io.h, and up till now we've always put that at the top of the program, and here's one where it works just fine, and it's not there. Can you explain that?
We aren't using anything from standard I/O.
Well, yeah, we are. We're printing stuff out.
Well, yeah, but that's included in the GPS.h or the GPS.c, sorry.
But that's compiled separately.
No. But
it's a head scratcher, right?
yeah. Well, does it get linked in because it's being used in GPS.c?
Let's try to compile GPS main just by itself. Now, I can't create an executable from it because it doesn't have all the pieces, but let's see if at least I can create the object file. The object file contains almost everything to make it an executable. It just doesn't include a little bit of bookkeeping stuff, and it doesn't include the stuff from GPS.c. But essentially we're going to do what the C compiler does behind the scenes, which is compile each one of the pieces separately. It compiles fine. That one compiles fine, and then we can bring them all together. And then run it. So no errors. So if you're stumped, the reason why is because that standardIO.h file doesn't contain any actual code. It's just function prototypes. It just tells the compiler about the existence of those functions somewhere else. And I'm not calling any of those functions inside of my main. I'm not calling printf. I'm not calling scanf. I'm not calling any of the file handling functions. I'm just calling printgps. So my main program here doesn't have to know about printf, and scanf, and fopen, and fclose. It only has to know about printgps, which is over here. Now, gps.c needs to include standardIO.h because it calls printf. And so the compiler needs to be able to know what does that function, what's its name, what's its parameters, and what does it return. If I take out this include from gps.c and save it, and I try to compile it, we're going to get a warning or an error that says, I don't know about this printf thing. You better tell me about it. So you only need to include header files that you actually need to get it compiled. GPS main.c doesn't need standardIO.h because it doesn't call any of those functions directly. It calls printgps, and printgps in turn calls printf, and that's why we need standardIO.h in that C file, but we didn't need it in the main one anymore. It doesn't hurt to put it there, but we don't need it. There was a question here, which is, could I put the struct declaration inside of the gps.c file? Could I take this here out and put it here? And is there a further question like, do I need to put this gps.h here? Well, until we get the answer to that is, what now is going to happen here? Is this going to compile? Let's play the game. Will it compile?
No.
Why not?
Because GPS main can't see inside of gps.c. So it's not going to know what a struct GPS is.
So that's your hypothesis, is that GPS main...
That's my hypothesis. It's a nice word for guess.
You can't look inside of gps.c and therefore doesn't know what the struct GPS is. And you're right. Declaration of struct GPS is not visible outside of this function. So I can't just put the struct only in gps.c because GPS main also needs to know about that struct. Here's a clarification. I was thinking more if you could separate the contents of the struct into gps.c, so gps.h would only contain the struct GPS without the brackets and float declarations. I guess the idea is, like, can I kind of like prototype the struct GPS the same way we can prototype a function? Like, can I just put in just kind of like the header of this and leave out the float stuff. Kind of like how when we prototype a function, we just put in the name of the function and its parameters and leave out the actual body. I got it. The answer there is no, we can't do that. And so that's the short answer. No, we can't. The long answer is the reason why these have to be here is that the compiler needs to know how much space does this struct take up, so that when it does things like push values onto the stack, it knows how much space to set aside so that other variables can fit around it. It doesn't have to know that for a function, because functions are kind of self-contained units of execution. All it needs to know is what are the types of the parameters. It doesn't even have to know the names of the parameters, because again, when it passes values into a function, it's going to push onto the stack the parameters, and it needs to know how much space to set aside for each one of those parameters. If it's an int, it needs to know it has to set aside 4 bytes for that. And if that int is followed by a float, it needs to set aside 4 bytes for that. And then if that float is followed by a double, then it needs to know to set aside 8 bytes for that. So it needs to know how big is that stack of parameters that it's going to pass into the next function. Once the function gets called, then the function itself pulls those values off the stack, and it knows how big each one of those pieces are because that's contained in the function declaration. The function declaration, you know, when it says character pointer s and struct GPSG, tells it how big that stack of parameters is going to be, because it knows the size of a character pointer, and it knows the size of a struct GPS, and it knows that struct GPS takes up 2 floats, which is a total of 8 bytes. Okay, so you can't just drop in a struct GPS like a prototype, because the compiler needs to know how much space that struct takes up in order to be able to push things onto the stack and pull things off the stack. It needs to know how much space to set aside for those things. Does that answer your question? It's all about giving the compiler enough information to be able to generate the code for that function, so that any functions that it calls or any functions that are calling it have the pieces to be able to like feed parameters in and get those parameters out, right? It needs to know how these pieces interlock together. All right, so where does that leave us? It leaves us with, we need to put the structure declaration inside of the header file and the prototypes. And the gps.c contains only the C code, and it includes the header file so that it too can get that structure declaration. It will also contain a function prototype, but that's okay. You can put prototypes and function definitions in the same file. All right, let's save everything and just make sure it all still compiles. And it does. Whew, so where does that leave us here? So we declared a function. We spent all the time doing this GPS function. Let's make another struct. Why don't we actually, rather than making another struct, why don't we amend this structure so that it contains not only the latitude and longitude, but also the name of the place? Notice that when I printed out that print GPS, I had to pass in its name separately. Why don't we put that into the struct itself so that all I have to do is just pass in the structure, and then it prints out the name of it and its 2 latitude and longitude locations. So what do I do here? I want to put in his name. What do I put in as his type? And there's two possibilities here. So I could just put in like character pointer name. This is a string, this is a float, and this is a float. Or I could do name and then in brackets put something like 20, which would be the maximum length of the name. Let me put both of them in here, just so you can see them side by side. You couldn't actually do this in real life, right? Because you'd have two fields with the same name. But I'm just putting them in here side by side. What do you think is the primary difference between these two declarations? What's different about them in terms of what gets stored inside of that structure?
So the first one is going to store those characters on the stack, and the second one, it's a pointer. So you're going to have to allocate memory or point it to allocated memory and then free that memory when you're done with the struct.
So let me repeat what you said. You said that the first one, the name itself is going to be stored on the stack. And in the second one, the name itself, the actual string, is going to have to be stored somewhere else. And then this one, what's in the struct, is going to point to that. Is that what you got there?
Yeah. Yeah.
So here's our picture here. We have our struct GPS, and we got name with the 20 in there, and we got latitude and longitude. And so when the compiler or the computer needs to go and lay out the memory for this structure, it's really just going to lay out the fields back to back. Remember, it doesn't lay it out in a two-dimensional grid. It just lays them out in memory, because memory is just a one-dimensional array of memory locations. And so this is going to get laid out with, most likely, the name, and then it's an array with 20 bytes, 20 characters. And then behind it is going to sit the latitude, and behind that is going to sit the longitude. And this is a float, which is likely to be, I think they're 4 bytes. And this is also a float. So when we declare a variable of type struct GPS, it's going to set aside a total of 28 bytes for this structure. 20 bytes will be for the name, and then 4 bytes each for the latitude and longitude. Okay, but the alternative setup was this other one. And this one will be set up, oops, I need to change this over here. This is character pointer name. This one will be set up with the name, latitude and longitude, just like we had before, except that name here now is going to be a character pointer. It's not going to be the actual name. It's just going to be the memory address of where the name is stored. And this is a float, and this is a float. So if a character pointer is 8 bytes long, this is going to be a total of 16 bytes of information. So where's the actual name stored? Where's like Amazon or Golden Gate Bridge stored? Well, that would have to be set up separately. You'd have to then make another string and have this one point to it. So in the first one, I could put the name itself right in the structure. And in the second one, all I'm storing is a pointer to the string, and I'd have to set up that string separately somewhere else, and then have this one point to it. Okay, so I wanted to kind of show you that because at this point in learning about C, it's really easy to think that these two declarations of name are actually the same thing, and they're not. This first one here sets aside 20 bytes to store the string. The second one here only sets aside space for an address and does not, by itself, set aside space for the string. You would have to do that as a separate step outside of the structure. Why would you use one over the other? Depends upon where you want to store that string. Do you want to store it in the structure, or do you want to store it outside the structure? If you store it in the structure, then we know that the string can be no longer than 20 bytes. If we store it outside the structure, now we've got the flexibility to be able to set aside a string that's as long or as short as we need it. Like if we got a place with a really long name, we could create a string that with a lot of bytes and we could store it in there. Or if we have a place with a really short name, we could create a string that only holds a few bytes and store it in there. In both cases, the structure just points to where that string is actually stored. So I'm going to say, for simplicity right now, let's skip this second declaration and just go with the 20 bytes in the structure. Okay, so now we've got to re-architect our program here, because when we declare a struct GPS of Amazon, we can't just pass in 2 values. We now have to pass in 3 values. And then our struct GPS GG, let me take this out here, we don't need those anymore. We can assign to latitude and longitude, but we also need to assign to the name. So I can go gg.name equals Golden Gate. And then my print GPS, I don't have to pass in that string as the first parameter. I can just pass in the structure itself, or at least that's what I want to be able to do. I need to go back and change the function, but this is what I want to be able to do. Just pass in Amazon and GG, and I don't have to worry about passing in a separate string. Okay, so I've re-architected main. Now let's go into gps.c, and we'll change this so that we only pass in the structure. And now we can just say g.name here, okay? And then we need to go into gps.h, and we need to change the function prototype. Okay, so that should do it. So let's just review what we did here. We've got GPS main, where we can create a GPS structure called Amazon. We pass in the string and the 2 latitude and longitude floats, and then print it out. Then we create a one called GG, pass in the latitude and longitude, or set the latitude and longitude, and also set the name, and then we print it out. Then over in gps.h, we modified the structure to include the name, and we're storing the name right in the structure. And then we modified the function prototype so that we don't have to pass in the string separately. And then finally in gps.c, we also modified the function declaration so that we don't have to pass in the string separately. And we also modified the printf function to access the name field within the structure. Okay, so that all looks good. Let's give it a compile, and we've got an error. This is where I'll pause for a moment and let you digest this error message, try to figure out what's going wrong. And if you don't know what's going wrong, maybe you could start by figuring out what went right, what worked, and then what didn't work. Sometimes knowing what went right can help you figure out what went wrong, particularly if you tried to do two very similar things. One of them worked and one of them didn't work.
Do you have to do string copy here?
Where? GPS main?
Instead of assigning it with a equal sign?
Yes. So you have to use a string copy here. Let's try that, and then we'll try to figure out why is that. Okay, oh, it says, well, I'll pause for a moment, let you digest this error message, tell me how to fix it.
That one does a good job. That was a good error message because it says include the header string.h.
Because we're calling string copy, main needs to know what is the name of that function, what's the parameters, what does it return. It tried to guess. It was an implicit declaration. It might have been right, but just to get rid of that warning, we will include string.h. And there, it compiled. And it ran just fine. Okay, so that was the fix, putting string copy in here. But why was that the fix? And why didn't we have to do it up here? So it gets back to the way that the variables are stored within the structure. We're using the first one up here. We're using this one here. So the name field contains the 20 bytes that are actually going to hold the individual characters of that string. Let me put it back the way it was before. When you write a program like this, with a string kind of standing all by itself, like here, that's considered a global constant. Right? This string is a literal string inside of your program. So the compiler is going to put that in the global constant section of your program. Remember that segment diagram that I've drawn a couple of times? Looks like a layered cake, and I'm drawing it kind of hastily here. This was the text segment, then the data segment, and the stack segment. And then within the text segment, there were two pieces. There was the actual program code, the actual ones and zeros corresponding to the instructions of your program. And then right above it is global constants. And then in the data segment, that was also split up into two pieces, you had global variables and the heap where your malloc stuff goes. And then finally in the stack segment, you have locals. Okay, so a string sitting all by itself is sitting here in this global constant segment. So when I do this assignment of gg.name equals golden gate, what it's attempting to do is just take the address of where this string is sitting in memory and assign it to this field called name. But the name field is not set up to accept an address. It's actually a type conflict. This is a character array, and this is a string. And doing the assignment here is trying to copy the address of where that string is sitting into the name field. But the name field is not a character pointer. It's not an address. It's an array of characters. And so we get that error message that says, where was it? Array type character 20 is not assignable. We can't just assign a value to that. Instead, what we have to do is copy the individual characters out of the global constant, Golden Gate, into the name field in the structure, one character at a time. So it has to run a string copy, as we've seen. It runs a little loop that just loops through the source string, copies the individual characters over into the destination string, and then when it hits the null character, it stops. So that's why we had to make this string copy. So it will copy the characters out of this global constant into the name field of the structure. But why didn't we have to do it up here?
That's what I was going to ask.
Well, that's because when you declare a structure or declare any type of variable and then assign to it on the very same line, if it's a string, the C compiler will turn that into a string copy for you.
Okay.
That only works if you are declaring the variable and assigning to it on the same line. If you separate those out at all, then it doesn't work. Okay, so if I did, whoops, I didn't want to do that. I wanted to do this. Here we go. If I did character name 20, and then name equals Barry, that's not going to work because the compiler is going to think I'm going to take the address of this string and put it into the name field, and the name field is not set up to take an address. But if I combine those onto one single line, the compiler will see that I'm trying to do this, and it will do the right thing. It'll copy the characters over for you. If we actually look at the assembly code generated, you'll see a little loop in there copying the characters over. Okay, so that's just a little, I don't know what to call that, a little twist on how strings are handled in the declaration line versus any other line in your program. Okay? Let's see. What if we did, someone's asking, what if we did star gg.name equals Golden Gate? What do you think about that?
C doesn't let you do that, right?
Well, I mean,
wait, star GG. Well, no, name is name's not a pointer.
So I'm hoping I got this interpreted correctly, but yeah, so we're trying to dereference. Now, as I said, I think last time, the dereference operator is way down on the precedence list. So the dot operator actually comes above it, which means it's not going to try to dereference GG. It's going to dereference name. So this is dereferencing gg.name, but name is not a pointer. Name is a, I mean, it's the actual array of characters. I mean, I can see where the confusion lies, because earlier in the semester I said that when you pass a string into a function, then when you pass in the variable, you're really just passing in the address. So you kind of think that strings and pointers are the same thing. but there is a subtle difference. That in one case, it's the actual like array of characters, the actual number of characters you set aside, and the other is just the address of the thing. So although name has an address, it's not declared to be an address, and so you can't dereference it. Now, if it was declared to be like a character pointer, then we'd probably be going somewhere, but it's not. So this is just not going to compile. Okay. Are we good with this? I mean, are we good with the way that we declared this structure? So if you declare a structure so that you got an actual string inside the structure, then when you want to move things into the structure, as long as they are primitive values like floats and integers, you can just use an assignment like you normally would. But if they are any kind of compound data structure like an array or a string, you're going to have to move things in 1 byte or 1 character at a time. In this case, using string copy. So if it's a primitive type, like a float or an int, then what the compiler does is it just takes this value and moves it into a register, and then it takes the content of that register and moves it into the memory location. It's very easy to do. But for a string, because a string can be kind of any length, it can't move that string into a register and then move that register into another string. It has to copy them over 1 character at a time. So are we good with this? Because I guess I'm going to change things up a little bit.
Yeah, that makes sense.
Okay. Let's go to the other declaration of this. Let's make the name inside of the struct be a pointer. Now, do you think it'll compile as it is? What do you think is going to happen up here? And what's going to happen here? We're playing the game. Will it compile?
Well,
it's kind of
probably
like,
not.
you ever seen those old YouTube videos? Will it blend?
Will it blend? iPhone dust. Don't breathe that.
So will it compile? And
well, probably not. If you change the type of something, it's probably not going to compile.
well, will the first one compile?
Well, that's a good
second
question because, yeah, I didn't know the compiler automatically copied strings for you. So what automatically
So
point
will
to
it
that?
now? Will it now try to copy this string? Let's find out. Oh, it compiled.
No, you didn't say. Wait,
That
where is it getting that GG name?
Right here.
No, it's the where it says blah 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 equals Golden Gate.
Mm-hmm.
Where is it getting that parenthesis star GG dot name? It's getting it from that.
I don't understand your question then.
Can you scroll up the error message one line?
Oh.
So GPS main line, it's saying line 15 is GG.
Oh, no, that's the old error message from like 5 minutes
I've
ago.
seen it. I'm sorry.
This is the new one here.
Compiled without, it compiled
No
without.
errors at all.
Oh. Okay.
Oh, it crashed. It compiled,
So
but
Amazon one worked.
Amazon worked. Golden Gate did not.
Okay. Well, it's because you tried to copy into something that's not a string array or a char array.
Okay, so let's try to dissect what happened here. First, let's figure out why did this one work.
Because the compiler's being nice to us, and it's just
Yeah, the
looking-
compiler's being nice. It goes,
Yeah.
hey, I noticed here that you declared name to be a character pointer. And just like before, Amazon is sitting off in the global constants section. But since you made this a character pointer, I'm just going to, and I am speaking for the compiler here, I'm just going to make name point to that global constant. So if it sees that the struct was set up as an array of characters, it'll do an implicit string copy for you. And if it sees that it's set up as a character pointer, it'll just make the pointer point to the string that's sitting in the global constants section of the program. So it does the right thing in both cases. It does what you expect it to do. And then, as we saw, it compiles. And the reason why it compiles is because we're passing in to string copy what string copy expects to be passed in. String copy expects to be passed in 2 character pointers. And name is a character pointer, because that's the way it's declared. And when it passes in Golden Gate, it just passes in the address of where that string is sitting in memory, which is over in the global constant section. So string copy gets what it expects, and that's why the compiler passes that through, because we are passing in exactly what string copy expects to receive. But it crashed. And I guess the question is, did it crash here, or did it crash here? We don't really know, because it didn't print anything out. So let's find out where it crashed. Let's recompile this with the -G flag so that we can run the debugger on this, and we'll let it run and crash. And now we'll go gdb a.out core. And it says here that it crashed inside of string copy. So we know that it crashed on line 14. And we could also do BT for backtrace, and we can see that indeed it crashed on line 14 of our program. So why didn't that work? What instigated this crash?
The value in name is a garbage value,
Right?
so it's pointing to who knows where.
Yeah, exactly. So the value inside name contains a character pointer, an address, and it's a garbage value, so who knows where it's pointing? It's probably, obviously, it's pointing off to some memory location that we don't have access to. We're getting a segmentation violation, so it's pointing to some address that we're not allowed to write to. And so the operating system terminates our program right there. And so the reason why is because string copy needs to copy the individual characters from, the second string into the first string. And the first string's address is pointing off into Never Never Land. So in this case, we shouldn't use string copy to do this, because we're not copying the individual characters from one place to another, because there's no place in our structure to receive those characters. So there's 2 things we could do. One is we could do like a malloc to set aside space for that string. And the second is, and probably the easier one, is, just go ahead and assign it. And then it will take the address of this string, again, sitting off in the global constant section, and just take the address and copy it into the name parameter, which is set up to receive an address. So compiles fine and runs fine. Okay. And so that was technique number 2. And I said the third technique was we could use like malloc to set aside space for that. And if you want, we can do that. We could do something like gg.name equals malloc. We could set aside 20 bytes for that. And then we would have to change this back into a string copy. And we do that so that it actually copies the characters out of the global constant string into that memory space that we had set up with using the malloc. So it's actually copying the individual characters over. What that means is at the end of this line 15, there's now going to be 2 copies of Golden Gate sitting in memory. There's going to be the one in global constants, and there's going to be one sitting in the heap. Same thing for Amazon. There's going to be 2 copies of Amazon, one in the global constant section and one on the stack, because this is a stack variable. Now we need to include standard library because we put malloc in there. Ah, you're right. Then don't forget to free the memory. Yeah, free.
Right.
Oh, what do I pass into free here to free up the memory?
gg.name.
Good.
Right. You pass
Right.
it whatever you assign malloc to.
Yeah, exactly. I'm not going to pass in GG because
That's on the stack.
that's actually on the stack, right? So you can't free that up.
And
Interesting. Like the GG
But you don't
structure
have-
is in the stack, but the string is in the heap.
But you don't have to free Amazon.name,
Correct.
right?
Because there was no malloc associated with that.
Right.
There was going to be a second part to that sentence, but actually that's the sentence. There's no malloc associated with that. Okay. I actually want to do one more thing that's going to blow your minds. I've been very careful to word everything I've said regarding these strings. So hopefully I've dropped enough hints over the last 30 minutes that you'll understand what's going on. So I'm going to change the letter A in Amazon to an X. Compiles, crashes. Didn't even get around to printing out Amazon or Xmazon. What happened? And then let me comment out this line because that was the only line that I added. So that must be the one that's causing the crash. But let me go down here and go gg.name bracket 0 equals X. Do the same thing. That one worked. Okay, so the first one, the attempt to change Amazon to Xmazon did not work. And the attempt to change Golden Gate to Xolden Gate did work.
I think I know.
Okay, hold on to that thought. Let's let other people kind of catch up. Why did that work for the second one, not for the first one? Abdul on YouTube says, because we have access to the second memory, but not the first. Let's be more specific about what you mean by access. Like, I can clearly print out Amazon. I just can't change it. And I can clearly print out Golden Gate, but I can change it. What's the difference? Kai
So
says,
one is read
does it
write.
have to do with where the string is held in memory? It does. And is that what you're going to say?
Yeah, so one's read write, one's read only. Golden Gate, we did a malloc, which gives us access to read write memory. Amazon is sitting in the global constants, which are constant. You can't change that.
Yeah.
You can't write to the global constant.
Those
area.
string literals that I have in my program are sitting in the global constant section down here. And this entire segment is tagged as read only. You're not allowed to change anything there. Any attempts to change anything there will result in an immediate termination of your program because you are doing something not allowed. You know, the worst thing you could do is actually just change the program code. You don't want to do that at all. Yeah, so attempts to change Amazon result in a crash because Amazon is a global constant and my structure, which is on the stack, my Amazon structure is up here in the stack, but that name field is pointing to the one that's in the constant. And so an attempt to change that is actually trying to change the one that's in the global constant section, and it results in a termination of the program. But the Golden Gate one, the GG structure, is also sitting in the stack. But we did a malloc, which sets aside a string inside of the heap. And then we copied Golden Gate into that string. But this is read-write. Data segment we can write to. And so we can change the string inside of that. So that's why that worked and the Amazon one didn't. And I'm bringing this up because this does catch people once in a while that, I can understand why you do that. You're falling back on your old Java habits, which is to take a string and just assign it to a variable of type string. But what's happening in Java is that string is not sitting in a global constant memory. It's actually sitting in the heap. And so you can assign it to a variable and then you can change it. But in C, there's an attempt to optimize your program. And so any string literals are sitting in the global constant section and you can't change them. You're free to assign them to string character pointers, but you just can't change them. If you want to change them, you're going to have to make a copy of them. So that's a really subtle little gotcha about why the program sometimes seems to work fine and sometimes it crashes. And it all has to do with where that string is occupied in memory. See, Java, because all objects are stored on the heap, and a string is an object, and all primitive types are stored in the stack, both of those sections of memory are read-write, and so you can change them. Very little stuff in Java is stored in the global constant section. Like, actual constants are stored there. Like when you say const and then a value, right? Then that gets stored there. But everything else gets stored in the heap or on the stack where you're free to change things. And so in some respects, Java kind of hides that from you, right? Everything appears to be mutable unless you declare it to be constant. Whereas in C, you have to be, as a programmer, you have to be sort of intimately aware of where things are actually getting stored in memory. Some things are going in the stack, some things are going in the heap. Some things are glowing in the global constant section. This is like probably a really good technical interview question. Why does this program crash here but not here? And if you have experience with C or C++ and you're aware of where strings get stored in memory depending upon how they're declared and how they're used, then you can answer that question. But if you come from a Java background, you might go, I have no idea. It works in Java. That's why I think it's a good idea when you're going through the process of learning to become a programmer. Don't just stick with one programming language. Learn as many as you can, because all of them, even though people will tell you, you know, Java and C and C++, they're all pretty much equivalent because they all kind of do the same thing. But how they do those things is just different enough that you ought to learn them so that you're aware of the subtle differences under the hood. And then these are the kinds of things that an experienced interviewer could ask you, because they want to know, do you know the difference between C++ and Java and the way it handles memory? Do you know what a segmentation violation is? Because a Java programmer is unlikely to run into that error ever, whereas C and C++ programmers run into it all the time. Do you know how to fix memory leaks? Doesn't really happen in Java programs because you got that garbage collector handling things for you. But C and C++ programmers have to handle that. Can you track those down? Can you find them? Oh, I'm not saying that's easy to do. It's really hard to do. There's like, have you ever noticed that Chrome, the browser, and Firefox, the browser, if you leave them running for days or weeks or even months at a time, they just slowly gobble up, not even gobble up, nibble up the memory of your computer to the point where they're using dozens of gigabytes of memory. And that's because deep inside the code for both of those browsers, there is a memory leak. It's a very slow one. It only leaks out like a few bytes per minute. But it will slowly eat away at all the resources of your computer to the point where things just grind to a halt after a couple of days or weeks, depending on how much you use your browser. Internet Explorer, I think, was also that way, and may still be that way, to the point where, I think it was maybe 10 or 15 years ago, Microsoft just issued a bulletin that said, we recommend you restart Internet Explorer once a day. And they had no idea how to fix this memory leak, but so the fix was just to restart your browser. And this was back in the day when restarting your browser meant all your tabs got closed, all your windows got closed, you had to start over again. And so I still find myself, if I'm leaving Chrome running for a long time, just periodically I have to close it and open it again. Unfortunately, I have like 30 tabs open, and all of them are important. Right? I can't close any of those. So I'm just kind of back to where I started. The nice thing about Chrome and Safari is that when you open up the browser again, it opens up all the tabs, but it doesn't load the pages themselves until you actually go to that tab. So even though in my Safari browser on my desktop computer, I've got probably at least 40 tabs open, only like 8 of them are actually active. And so I'm hoping that kind of keeps the memory usage down a bit. Okay, so we got through structs, basically. And we learned about how to declare structs and how to access the fields within the struct and how to assign to them and how to pull things out. I mean, you pretty much know everything there is to know about structs at this point. So I'm thinking, why don't we take a little break, 5 or 10 minutes, and then we could talk briefly about arrays of structs if you want, or I can show you some other little nifty things about structs that you can do.
Recording stopped.
I'm just pausing the Zoom recording. Oh, let me see if I can catch up on some of these comments or whether we've already got them. Can we make a function to print coordinates using degrees, minutes, seconds format? I suppose we could. We would just have to do the calculation to turn the fractional portion of the degrees into minutes and seconds, which, divide by 60. Something like that. Get the remainder and divide that by 60 to get the number of seconds. Oh, you're taking a data structures course, so this stream was very good for me. What programming language are they using? And I should actually not say they, I should say you. What programming language are you using in your data structures course? Oh, you're using C. Okay, well, so this fits right in. I don't know if this is still the case. This is totally an aside. I don't know if this is still the case, but in C++, structs and classes are pretty much the same thing, with the difference that in a class, the fields and methods are private by default, and you have to make public the ones that you want to make public. And in a struct, the fields are public by default. And when I say equivalent, it means that, and this was at least the case 20 years ago. I don't know if it's still the case now. But you could actually declare a class using the word struct instead. Put all your methods in it, put all your fields into it. It's just that everything will be public by default, and you have to tell it which ones are going to be private. And then a class, you declare a class, you put all your fields into it, all your methods in it, and then everything's going to be private by default. You have to tell it which ones are going to be public. So in C++, and like I said, this was at least true 20 years ago when C++ was kind of like somewhat new, they were essentially equivalent to each other. I don't know if that's still the case. Maybe the compilers have gotten better to the point where they kind of frown on putting methods into structs or putting the access adjectives like private and public into the struct. But like I said, at least when I was learning C++, it's got to be more than 20 years ago, 30 years ago. When I was learning C++ 30 years ago, it was actually really confusing for us because we didn't understand this whole object-oriented thing. It was a new concept, and we struggled with, when do we use a struct? When do we use a class? Like, does it have to do with whether you want things public or private? We just kind of like, we meaning like me and my classmates, were just kind of like, don't know. Can we make structs have a default value instead of garbage values? Not, well, I don't want to just say no. Because I'm thinking there's two things you can do. One is the default behavior of the compiler is that anytime you declare a variable or a struct, you just get garbage values because it's faster for the compiler to do that. It's faster for it to just simply set aside the memory and then not worrying having to put zeros into that memory locations to clear it out. That's what Java does for you. That when you declare a variable or an object and you don't have a constructor for that object, it will just put in zeros for you. It'll put in false for booleans and zeros for integers and floats, and any things like strings or object pointers will just get the value null. Basically just a bunch of zeros. But C doesn't do that. C just simply sets aside the memory. It says, okay, I know the struct is going to take up 28 bytes, so I'll just allocate 28 bytes on the stack, and whatever happens to be on our stack is just what's there. So one thing you can do in C is you can do like what we had was struct GPS Amazon equals, and then in your curly braces, I think you can just put a single zero there, and it will automatically fill the rest of the struct in with zeros for you, I think. I'll have to go research that. And so that would be solution number one, is when you declare a struct, at least put in like little braces and put a 0 there. And then I think it'll fill the whole thing in for you, I think. But the other thing I was thinking about was maybe there's a flag you can pass into the compiler that will tell it to initialize variables with zeros and nulls for you automatically. And then it will just expend the extra cycles to do that. Well, let me find out. Can GCC or Clang initialize variables to 0? I'm reading some Stack Overflow stuff. While I'm reading this, I will tell you that I've been showing you malloc, which just simply sets aside a chunk of memory for you, and then whatever happens in that memory is what it gives back. There is a similar function called calloc, C-A-L-L-O-C, and it will initialize that chunk of memory to 0 for you. So it does actually take the extra time to go and zero out that chunk of memory that it just allocated for you. So if you use calloc instead of malloc, you'll get all zeros, but that only applies to memory that you allocated using the allocator. It doesn't apply to the stack variables. Also, the parameters to calloc are a little bit different. Yeah, so the parameters to calloc, you pass it 2 parameters. You pass it how many things you want and what's the size of each. In malloc, we did that by just multiplying the 2 things together. We did the number of items like 5 times the size of int. But in calloc, you just pass those in as 2 parameters. It takes care of multiplying them together for you. And then it will zero out the memory. All right, so back to where I was. Can we pass in a compiler flag so that stack variables automatically get initialized? So the one thing going against a potential compiler flag is the actual C language standard says that when you declare variables on the stack, they will not be initialized for you. And so the danger of providing a compiler option is that it means that if you take that program and you compile it using a compiler that understands that option, then the variables will get initialized for you. And if you take it over to a compiler that doesn't understand the option, the variables won't get initialized for you. And so you as a programmer may fall into a trap of feeling like the variables are always going to initialize, so I don't have to worry about that. And in fact, you do, because if ever that program is taken over to a compiler where it doesn't initialize for you, then you can run into trouble. I'm doing some reading here. So it looks like there might be a flag called 0init, and you can pass it either on or off. But it says, this is only for the Texas Instrument compiler. I'm looking for GCC. I'm not seeing anything. Nothing is just jumping out at me. So my guess is that, at least for GCC and Clang, they do not support automatically initializing variables to zeros. In part because it's part of the C language standard that says, don't do that. Don't automatically initialize. That's just the way C works. Whereas it's part of the Java standard that says that variables will get initialized. Oh, I see what your question is. Your question is, can we specify default values for structs so that when we do initialize it and we don't explicitly set the values, they could have a value? Well, let's go and try. So what you're saying is, can we do something like this? Let's see, will that compile? No. You cannot assign to a field within a struct inside of its declaration. So that means you can't give struct members a default value. The error message here is telling us it expected to see a semicolon at the end of the declaration, and instead we passed in a equal sign. So this is not allowed. That means that struct declarations can only contain variable declarations, and they cannot contain assignments at all. And this may be a C thing. Maybe C++ allows it. You know what? I'm going to try. I'm going to put this back, and I'm going to do an experiment. So I'm going to save that, and I'm going to compile it with the C++ compiler, which I think is called G++. Yep. And let's compile gps.c, and let's use -c on there. And that compiles. So C++ allows a default value for struct numbers, and C does not allow it. Let's also try Clang++. Warning, treating C files as C++ when in C++ mode this behavior is deprecated. Deprecated is a fancy word meaning this is no longer supported, but it's still there for compatibility reasons. And it may be removed at any time. Okay, so Clang++, which is the C++ compiler for Clang, does support assigning default values to a struct, but Clang itself, the C compiler, does not. So if we go Clang, let's go G++. G++, gps main.c and gps.c. Ooh. All right, so attempting to compile my program using the C++ compiler now generates all sorts of other errors. It's not really true what people tell you that C is just a subset of C++ and that any valid C program is also a valid C++ program. That is not the case anymore. I think, probably used to be. And I say probably used to be because the way that C++ compilers used to be implemented was they were just a front end to the C compiler. The very first C++ compiler that I used back in the early 1990s was literally a C++ to C compiler. It would take your C++ program and turn it into valid C code and then run it through the C compiler. And that meant that any valid C program was also a valid C++ program, because then it would just take your C program and just pass it through unchanged, basically, to the C compiler. But that's not the case anymore. C and C++ have diverged enough that C programs are no longer just a subset of C++ programs. Why don't we stop it there?
Recording in progress.
So when we left off before the break, I mentioned we might do a couple of things. One is some little tricks that you can do with structs, and the other was how can we create an array of structs. And normally this would be our programming assignment time, but we don't yet have enough information to be able to do the assignment. So I'm going to defer that until next week, and then we'll really kind of get started on that assignment. And then you'll have enough pieces. You can go ahead and you can look at the assignment, and you can try to start taking a stab at it. So the first thing I wanted to show you here was, how when you declare a structure, the type ends up being two words: struct GPS, or struct person, or struct whatever it is. And you say, like, well, I don't want to type those two words all the time. So you can actually, I don't know if I've shown this to you before, but you can create an alias for any existing type. There's a keyword called typedef. And you can take any type and give it a new name. I'm actually going to do this inside of main first here. So, and I'm not going to show you this example with structs just yet. So I can take any existing type like int, and I could call it something else. Let's call this, I don't know, let's call it centimeters, right? cm. So now now basically I've declared a new type called cm that behind the scenes is just an int. So I can now declare types of that type. I can go cm height. And I can go like height equals 50. And let's see if that'll compile. And it will. So I've now created a new type called cm, centimeters, that really behind the scenes is just an int. Typedef, the name of the existing type, and then the new name. Okay, so that's how typedef works. And if you've used something like standard int, there we go, standard int.h, that gives you types like uint 32_t. And this is C's way of trying to be portable behind the scenes, this is just an int or an unsigned int. So anytime I type uint32 underscore t, it's actually just swapping in unsigned int. Or if I have, let's do, oh, I don't know, long int64 underscore t. So anytime I type int64 underscore t, it actually just swaps in a long, which is 64 bits long. Okay, so that's what standard int does, is it gives you these portable ways of declaring data types of a specific size. And the uint32 is going to be a different declaration depending upon what architecture you're on. If you're on like an Arduino, those little tiny 8-bit or 16-bit processors, then the integer is not going to be a 32-bit quantity. It's going to be a 16-bit quantity. So in order to give you a 32-bit quantity, it has to turn this into an unsigned long on the Arduino. So this standard int.h header file is different depending upon what architecture you're on, with the goal of, as a programmer, you can just say uint32 underscore t, and you will get a variable that can hold 32 bits of information. And behind the scenes is just going to swap in whatever data type happens to work for that. Okay, so that's type def. So you can take an existing type and give it a new name. So let's go into our GPS file. And here we can say type def. We'll give it the existing name, which is struct GPS. And then we'll give it our new name. And I'm just going to call it GPS. So every time I type in GPS, it's just going to swap in struct GPS, which is the actual name of the structure. Okay, then I can go back over here to my GPS main, and I can take out all this struct stuff. And it compiles. Okay, so what did I do there? I declared my structure. That part didn't change. And then I created an alias for it. I created the alias called GPS, and anytime I type in GPS, it actually swaps in struct GPS, which is the whole and proper name for the structure. So that's kind of cool. You can declare a structure and then create an alias for it. What you're going to see as C programmers is people combining these two steps into one step. They do it like this. They put type def in front of the struct, and then they put the alias back behind it. And it works, compiles. So here we're just combining the struct declaration and the type def statement into one line, one block, by putting type def in the front, then the struct declaration, then the alias behind it.
So then on that line 9 there, you could take out the word struct?
Yes.
Okay.
Mm-hmm. And the name of the alias doesn't have to be the same as the name of the struct. It's just, I just do that for convenience sake. But you can call this whatever you want. Now, every time it sees aardvark, it's going to swap in struct GPS. I kind of worry about the people watching on YouTube who aren't from the United States. Like, do you know what an aardvark is? And I don't mean, I'm not trying to be critical or anything. It's just that I know that some animals we use here in the United States just don't exist in other parts of the world, or they have different names. And so, here in America, aardvark is just a funny sounding animal name. So, I like to use it because it's just goofy, right? But is the aardvark actually native to America? And if it's not, where does it live? And what name is it? And I don't see anyone on YouTube speaking up, so maybe they're looking at me like, I don't know what an aardvark is. We also call aardvarks anteaters. That's what they look like. Okay, so that's structs, and the little interesting thing I wanted to show you was how to create an alias for a struct, so you don't have to use the whole name every single time. So how about an array of structs? Let's say I want to store information about a series of landmarks, right? I want to have sort of latitude and longitude and the name of some famous places around the world. Now, I've already got my GPS.h. That's kind of nice, right? We've got our print GPS, we've got our struct. All we have to do is create an array out of these things. So let's make a brand new main. I'm going to keep this one. Let's make a brand new one called landmark. In which I'm going to store some information about, let's say, 4 or 5 famous landmarks. So while I'm kind of typing in some of the template code here, go ahead and put in the chat the name of some like famous places, and then we'll look up the latitudes and longitudes. And if you can take a moment to go into Google Maps and look up the latitude and longitude, that would help a lot. So let's create an array of GPS. And you create an array of structures just like you create an array of anything else. You put the type, and then the name of the array, and then how many things you want to store. Let's say it's 5. So with this line here, I have set aside space for 5 GPS structures. So it looks like this. We got 5 boxes, and inside each box we have a name, we have a latitude, and a longitude. And it continues on for the other boxes. So let's put the, what do we got here? We got London. Let's put London into box number 0. Now, because we're not declaring the array and storing items in it in one single statement, we can't use the trick of using the curly braces and then putting all the values in there. We're going to have to do each one of these separately. So landmarks 0 dot name, okay, so indexing into the array, getting box number 0, and then within box number 0, going to the name field in there. Now we can do this. We can do this because this string is stored over in the global constants area, and we're just going to copy its address into the name field. And if you remember, the name field is set up to accept an address. So this is okay. If we had declared our structure to be the string itself, like name bracket 20, then we would have to use a string copy to get those values in there. But because it's set up to accept an address, we can just do an assignment here. Remember the downside of this. You can't go and change the name because this is pointing to a constant. Latitude is 51.57, and the longitude is very close to 0. And then the next one we've got here is Tower of Pisa. Pizza? 43.7229 and 10.3965. What a longitude. Eiffel Tower. Oh, this should be name. Eiffel Tower's latitude is 48.858, and its longitude is 2.292. See how we have to do each one of these individually? Because we're not declaring the array and the structures in it and assigning to them all in one statement. We have to do these each individually. We can't do anything like landmarks 3 equals and then in curly braces because the structure has already been set up in the array. It's already set aside all the memory for that, so we can't even just assign to the structure using the curly braces. We have to do it one piece at a time. Ayers Rock. And we're going to do one more after this because we have 5 things set up. Latitude is negative 25.344. And longitude is 131.037. And the last one. North Pole. Latitude is 90. And what is the longitude of the North Pole? I mean, really?
Infinity.
I mean, could be 0, you know,
Be anything,
but
yeah.
could also be 45. Could also be this big number, although you go around and around and around the North Pole many times. Someone in the chat says, just put 0. Okay, so we've defined our 5 landmarks, and now let's print them out. So for int I equals 0, I is less than the number of items, I++. Okay, what do I put inside this loop?
For GPS.
Yeah, let's just call print GPS. And what do we pass it as a argument?
Landmarks sub I.
Landmarks I. Very good. Oh, what did I do wrong here?
Or int I equal to. I don't know.
Let's go up.
Oh. It was up there. Unexpected semicolon for close.
There's no semicolon after the define, right?
That's right. This semicolon should not be there.
Wow.
What happens if we put it there? Why is that an error?
Oh, because down where it says GPS landmarks n items, it's substituting 5 semicolon for n items.
It's literally just a copy and paste, right? Anywhere where it sees n items, it puts in this thing, which is 5 semicolon. So
yeah, that's one of those error messages that's kind of confusing.
And it also means down here where we have n items.
Oh, this is an extra semicolon.
An extra semicolon. And it doesn't quite know what to do with that.
Yeah, defines are kind of little landmines of potential errors.
And that's why, well, let me run the program and then we'll talk for a moment here. Hey, it worked. So I can print out an array of structs just by leveraging that print GPS I already have that prints out one struct. All I got to do is wrap it inside of a loop and then call it for every single element of the array. I'm going to put n items back here. Yeah, so you were pointing out that the compiler didn't really catch that the problem was due to the define. I mean, there's like this little maybe note here that says there's a macro called n items, and it's pointing at that semicolon there. But you know, if you just look at the other error messages, you don't really know. Like you're going like, why is it pointing here about the semicolon when there's no semicolon there? It's way over here. And you know, what's going on here? What's wrong with this semicolon? That's the same semicolon I've used a dozen of other times in my programs. What's wrong with that one? And what's wrong with this parentheses? You know, so it's just like you got all sorts of problems with your for loop, and you're like, that's the same for loop I've been using, you know, for a long time. What is wrong with this? And it's all because, really, by the time the compiler gets to your program, the preprocessor has already done its job of swapping in that 5 semicolon for any occurrence of n items. But it's not shown to you here, right? You still see the original n items code, and you don't know that what's actually happened behind the scenes is that 5 semicolon went in the place of it. It's just not obvious here. And I think that's why, for things like constants, specifically numeric constants, C introduced the idea of a actual constant. Right? I can say const int n items equals 5 semicolon. And now that's an actual line of C code versus a copy and paste for a define. With the define, the C preprocessor will handle swapping in the value of the macro, the value of the name, behind the scenes for you. Here, this is not a preprocessor directive. This is an actual line of C code. Anywhere where the compiler sees that you have the word n items, it's going to replace it with the value of that constant. This is kind of like a variable, except that the variable doesn't change. So this variable is now stored in the global constants part of my program. So that compiles just the same. You can say I've got a constant, here's the name of it, and here's its value, and there's a semicolon sitting at the end of there. So now you're not going to get caught by weird syntax errors because it's able to check the syntax of this statement and make sure that it's syntactically correct. It's also going to catch things like, you know, if I put in aardvark here, it'll catch that. It won't compile because it says that you're trying to assign a string to something that's an integer. Whereas if I do a define, and comment out this is likely to generate, you know, the same sort of kind of weird error messages that we saw before, where it's not exactly clear what's going on because the C preprocessor did its work ahead of time, and now the compiler is stuck going, what's this variable or this string called aardvark doing inside of the square brackets? So it's not really possible to check the syntax of this define because it's just simply a copy and paste. Whereas with the constant, it is possible to check the syntax and check the types and make sure the type of the thing that you're assigning to it matches the type of what you declared it to be. So I think the preference now is use these constants rather than defines to do things like numbers and strings. But you still see a lot of programmers still using the hashtag define because that's the old way of doing things, and it's guaranteed to work on every compiler. Even the old compilers did it that way. The constant wasn't introduced until later in C's heritage. Does that make sense? Right? So they fill the same role. They fill the same role of being able to declare some kind of global constant. It's just that the const int can be type checked and syntax checked, and the define can't be until it's kind of like too late. Nevertheless, you can do some very interesting things with defines. Like, you know, you can define pretty much anything to be anything else. Like, something weird I could do here. I could say, anytime we encounter the letter or the word G, capital letter, just swap in GPS. And so now I can put G there. Oh, I need to change this back to 5. And it compiles just fine, right? So anytime it sees G, it's just going to swap in the word GPS and then go about its business. And then I could say, anytime I see the letter L, just swap in the word landmarks. So I'm now not declaring a variable called L. I'm still declaring a variable called landmarks. It's just that I now have kind of an alias for it, and it compiles just fine. Notice that in my program here, when I encounter landmarks here, I don't actually have a declaration for landmarks, right? It's now called L, but the preprocessor swaps in landmarks wherever it sees L. So I can use the two of them interchangeably. Boy, that'll really mess with people's minds, right? I mean, you can define pretty much anything to be anything else. Compiles just fine. What did I do here?
You made your program impossible to understand.
Anytime it sees a start, array start, it just swaps it in. It swaps in a left bracket. Anytime it sees a end, it swaps in a right bracket. And I have to put spaces around it so that it doesn't think that the end items is actually part of the name of the thing. Let's see, does that still work? That still works.
Yeah, so you could have L open bracket 0 AN and really make it cryptic.
No, say that again.
So on line 15,
Yeah.
just replace the closed bracket with AN. Yeah.
Can we turn in our programs this way? Create a little puzzle for you.
Um, Sorry for that blast in your ears, but it still works fine. Was that crazy? So anywhere where it sees loop n items, it just swaps in this little chunk of code.
Can you put those in the header?
This one here in the header file, like
All the defines?
Yeah. And then it's just as though they were in my program. If you're an old Pascal person, you'll do this. Oops, made an error. Compile's fine. And then you can start getting creative. Like, as if this wasn't creative enough, right? Let's see, what could we do with this? Get really creative.
Defines can't take parameters, can they?
They can.
Okay. So you could
I could go define loop I, comma, max as for int, actually let's call this var, int var equals 0, I is less than max,
var is less than
var
x.
plus plus, yeah, var is less than max. What, did I give it a name? Capital loop I, comma, and items. Compiles, runs. So now you go like, I don't like the way C does its for loop, so I'm just going to write my own.
Well, just because you can doesn't mean you should, right?
That's correct. But it turns out in a lot of C dialects, you know about this, the functions like is upper and to lower for converting case, those are actually just defines. So they look like functions that take in parameters, but they're actually just a define with a bit of code that actually does the translation, uppercase, lowercase. So you can take this stuff to extremes. There is or was a competition called the Obfuscated C Code Competition, or Obfuscated C Contest. Obfuscate means to make something unintelligible, right, by sort of like scrambling it up. And you can go back and you can look at some of the really old stuff. Oh, let me look for a good one here. Ah, here we go. So here's some code with a whole bunch of defines. So everywhere you see P, that actually means struct C. Everywhere you see Q, that actually means struct B. Everything you see H, it actually means this thing here. And so you look here at this code, and you know, it's all a bunch of copy and paste. That's not a great one. Oh, here we go. This is great. Everywhere where you see this, swap in this. Everywhere where you see this, swap in this. Everywhere you see this, swap in this. Everywhere you see this, swap in this. Now, some of these programs, because the C language has evolved over the years since the 1980s, some of these no longer compile under modern compilers. So you'd have to find an older compiler. Oh my goodness. So let's see, everywhere where you see main and then two variables, swap in the second variable. So what this person has done is they've taken basically everything that looks like a call to main is actually a function call to something else. So this main here is not the start of main. Oh, there's another main. Here's another main. There's another main. Everywhere where you see main is actually calling a function. So it's kind of fun to go through some of these. This program is valid under C, Fortran, and Shell.
Yeah.
Trying to look for some of the really good ones. Really, really good ones. What does this one do? That's the entire C program. This person here wanted to try to write the shortest C program they could, and this is what they came up with. So how does that work? We can actually do that. I don't know what to call this. Let's call it short. It's the shortest C program. Oops, I didn't want to do that. I wanted to create a new file. Let's call it short.c. P. Save it. So if I try to compile this, of course it's not going to work because I don't have a main in there. So what you do is you define what P is on the command line. So let's define P to be int main parentheses parentheses. Oh, and then short.c. Okay, now that works. And when we run it, of course, it doesn't do anything. But what it did is we told on the command line, everywhere you see P, just swap in int main and then opening and closing parentheses, and opening and closing braces. And now we got a program that doesn't do anything. And so we can change our compile command so that it does like a printf quotes hello semicolon. Oh, and it doesn't know what printf is, so we'll have to put in our include, but we can actually do that from the command line. I think I can do that. No, it's dash include. There we go. And now it prints out hello. So I'm basically passing the entire program in on the compile line, thus making this the world's shortest C program.
Does it even need the semicolon?
Maybe not. Let's see. No, technically you don't need it. But I think he wanted to get away with not having to put that ending semicolon in the program. Anyway, so that's how that program works. Oh my goodness, what is that? So part of this contest is trying to figure out what does the program do before you actually compile it.
It's all pi.
Here's the trick of using a bunch of defines to obfuscate what the program does. I'm looking for one in particular. I think I may have already passed it. No. I'm going to go back down. I think I passed it. So we looked at that one. This one? Oh, that's kind of fun. Just using O's and underscores for everything. They even defined O to be define. Nope. Ah, this one's a little fun. It's in the shape of a train. Nope, not looking for that one. Ah, here's one. This one, if you compile it, is actually a ASCII to Morse code converter. And, of course, it's written in essentially Morse code. No, that's not the one I'm looking for. I'm looking for one in particular. This one? Ah, yes.
Oh, it's all palindromes.
Yeah. And the program is written as a palindrome. After a while, after a couple of years of people doing this stuff here, of just defining macros to be parts of the program, they basically made a rule that says you can't do that anymore. That's no longer considered to be creative enough. And so as you get later and later in the years, they basically outlawed that. No, here, they're still doing it. Huh, I don't know what this one does. It's just a bunch of text. Looks like a Mandelbrot.
Mandelbrot, yeah.
And that's probably what the program actually does. So as you go later and later in the years. SoundX, that's a pattern matching algorithm. It's for doing strings that sound like other strings. You know, when you go onto Google and you mistype a search term and it says, did you mean this other thing that sounds similar? They're using an algorithm like SoundX to do that. Anyway, that's enough of that. So we've reached, oh, it's past 12 o'clock. So we kind of got an idea about how to do structs and arrays of structs. And this is going to be almost all of the pieces that we need to be able to tackle that larger program. The larger program just needs 2 extra pieces, and that's how do we sort things and how do we search through them once we've sorted them. So I'm going to show you next time how do we search through things, and then we'll learn how to sort them and then search through them. So we'll start out doing like a linear search where we start from the beginning and go to the end, and then we'll do a binary search. And along the way, we'll be searching things like arrays of structures. So if you've got an array of, let's say, information about people, first name, last name, and their age, and you want to be able to search for someone by their first name or search by their last name. If you want to be able to sort them, you want to sort them by first name, you want to sort them by last name, you want to sort them by age. There's ways you can do that. So we'll be looking at all of that next week. And then that'll give us all the pieces we need to be able to tackle this very last program. Okay? So that's where it leaves us today. I'm going to try to catch up this weekend on some of the recording your scores. I've fallen a little behind because I'm busy doing like video editing for another class. But I'm going to try to catch up this weekend. And that's it. So no new assignments this week. Use this time to catch up on any assignments that you still have in your to-do list. And then we will look at the last password cracking assignment next week. And then the week following that, we'll start in on computer networking. But the two units are going to overlap a little bit because while you're working on the password cracking one, we're going to be introducing the networking concepts. And you might still have questions about the password cracking program while we're doing the networking. Now, I have no problem with that. If you come to class, come to the session on Monday or Wednesday, and you say, hey, I got my password cracking program mostly working, but there's a bug. Can you help me fix it? That'd be a great time to do it. Just come to the session. We'll put your code up on the screen, and we as a group will look at it and try to figure out what's going on. I think group debugging is really instructive because it helps all of us be able to look at a program we didn't write and try to find the bug in it, which is really what a lot of you'll do as professionals, is you'll be looking at code that someone else wrote, and you have to fix a bug in it. So come back to the session on Monday or Wednesday, and we can do that. Now, someone says, obfuscation is good for JavaScript if we don't want users to know what a block of code does. Yeah, you can get JavaScript obfuscators. You write your JavaScript code for your web page, and then you run it through one of these obfuscators, and it does stuff like change variable names into just random strings and change function names. And it puts in all sorts of, in some cases, it puts in just dummy do-nothing statements that are just there to hide what the actual code does. You can also get JavaScript compressors that'll take your nicely formatted, nicely written JavaScript code and scrunch it down to be as small as possible. And part of the ways it does that is it takes your variable names and turns them into like single characters. So you have a variable, you have a function, let's say called print entry. It might just swap in the letter X for that function name. So it's now hiding from the user, hiding from anyone who's looking at it, what that function does, because it no longer has a name that makes sense. It's just called X. And it takes out all the spaces, takes out any character in your program that is not technically necessary to make your JavaScript code run. It pulls all that stuff out and renames things so all the shorter names, and it just crunches your code down so it's really small. Could also do things like reorganize the code, put it in a different order so it's harder to kind of decipher what it does. So lots of stuff you can do with obfuscators. Okay, well, I think I got to wrap it up here. I want you to have a great weekend and work on your programs, and we'll be back on Monday.
All right, take care.
Take care. Bye-bye.
Thank you.
Record.
And same thing for the YouTube folks. I gotta go. We're way over time. So I will, glad you could come around. We had a good question. Glad you could come watch the stream. We had good questions today and lots of good input, a lot of good chat going on. And I'd like to see lots of that. So we'll be back next week. Take care, everyone. Hope you have a good day. I know for some of you it's kind of late, so go to bed. Have a good one. Bye-bye.